We will look at Rolle's theorem and the mean value theorem. Our objective is to understand and use Rolle's theorem, understand and use the mean value theorem. Now, as a reminder, a theorem is something we can just use. We don't have to ever prove them to anyone. So you can just take a theorem and use it. Okay. But sometimes you will prove theorem to show you that the theorems actually work. So let's just recall something that from section 4.1 that we talked about, which was the intermediate value theorem. So if you recall from the prior section, the extreme value theorem states that a continuous function on a closed interval AB must have both a maximum and a minimum on the interval. Now keep in mind that both of these maximum and minimum could be at the endpoints of the function. So Rolle's theorem now gives conditions that guarantee the existence of an extreme value in the interior of a closed interval. Okay. So if we look at the definition of Rolle's theorem, okay, it says let f be continuous on the closed interval AB and differentiable on the open interval. And if f of A is equal to f of B, then there is at least some C, some value in the open interval such that f prime of C is 0. Now keep in mind the C value here is some X value we're referring to. So if we look at a picture of this, you'll actually see quite clearly what they're referring to. So I'm going to just draw a little picture, okay, or a graph. So if we look at this x-axis, and we have our y-axis, and let's say that here is A, and here is B, and we draw our graph. Let's do a parabola. It's a closed interval. Closed. So keep in mind that these here are closed interval, which is the interval A comma B. Okay, because of the endpoints here, the interval is closed. Okay, same thing here. So f, this is the function f. F is continuous, right? If I put my pen, I trace the function. Okay, my pen does not raise up at all, so it's a continuous function. Yeah, and it is differentiable on the open interval. If f of A, so if we take the function and we plug in f of A, okay, let's call this value here P. So notice f of A is equal to P, and f of B is also equal to P. It's the height of the function. Therefore, f of A is equal to f of B in this scenario. Okay. And if this ever happens, then there is some C value, okay? There is some C value there is a C value in the open interval such that f prime of c is equal to 0. And what this just means, okay, is the slope at c is 0. So if you look at this point here, tangent line there is 0. Okay, and that's really what the Rolle's theorem is telling you in words, and from a graphical perspective you see what it is. So you can think of any graph where this is possible. Try to make up a graph and see, once f of a is equal to f of b, then the slope is 0 at that point, at any at c, some c value. So let's look at an example and see how we can show what's happening. Let's look at this example. So given f of x is equal to x squared minus 8x plus 5 on the closed interval, let's say 2, 6, okay, determine whether Rolle's theorem can be applied to f of x on the closed interval. And then also, if it can be applied okay, find all value or values of c in the open interval AB. Okay. So let's see if it can be applied. So the first part we want to look at is to determine if Rolle's theorem can be applied to f of x on the interval. So to justify, to check if Rolle's theorem applies, we want to know what is f of a equal to and what is f of b equal to. So given f of x is equal to x squared minus 8x plus 5, and the endpoints on the interval 2, 6. So f of 2 is equal to 2 squared minus 8 times 2 plus 5, which is 4 minus 16 plus 5, which is negative 12 plus 5. And this is equal to negative 7. Now, so f of 2 is equal to negative 7. Now, if we try f of 6, this will be 6 squared minus 8 times 6 plus 5. So this is equal to 6 squared is 36, 6 eighths of 48 plus 5. And this is equal to minus 12 plus 5, which is equal to negative 7. So f of 6 is equal to negative 7. Therefore, f of 2 is equal to f of 6. Okay. So this part justifies. So now, okay, now we know that there is some c value, okay, if differentiable at c. So that's what we have to check now. Is this function differentiable? So if we look at another example, I want to show you what happens in this scenario. So let's look at, I know I missed the piece there. I was just thinking of a function. So let's say we have a function, f of x equals 3 minus the absolute value of x minus 3. And what we're going to do here is look at the interval here, closed interval 0, 6. Okay. So automatically you should know that you should look at this and say that this is not going to work. Okay. Because the function is not differentiable at every point. Now, what we care about is the interval here. Okay. So how do I look at this and I know this function, this will not work? Well, because you know what this function here looks like. This is the absolute value function moved over 3 units to the right, moved 3 units up, and then it's inverted or reflected because of this negative here. Okay. So if I had to draw this graph, a rough sketch, you don't have to be perfect. 1, 2, 3, 1, 2, 3. Okay. So the graph is moved over 3 units to the right, then up 3, but it's also inverted. So my graph would look, it's an upside down V. Okay. Now at this point here, okay, which is the point 3, and 3 is within the interval 0, and let's say some point over here 6. This function is not differentiable. Okay, not differentiable at c equals 3. But let's do this. So we were given here, you were given f of x is equal to 3 minus the absolute value of x minus 3 on the interval 0, 6. See, most students will just talk, well, what is f of 0? Well, f of 0 would be 3 minus the absolute value of 0 minus 3, which is equal to 3 minus the absolute value of negative 3. The absolute value of negative 3 is 3. So 3 minus 3 is equal to 0. So f of 0 is 0. And then what you continue to do is, what is f of 6? Well, f of 6 would be 3 minus the absolute value of 6 minus 3, which is equal to 3 minus the absolute value of negative 3. The absolute value of negative 3 is 3. And then you have f of 6 is equal to 0. And then you proceed to say, well, f of a, or f of 0, is equal to f of b, which is both equal to 0, and says, oh, Rolle's theorem will work. Rolle's theorem will work. This just shows that f of a is equal to f of b. Okay, this value here is a 6. But f prime of x, not possible. Okay, it is not possible because at x equal 3, okay, at x equals 3, the function is not differentiable. Okay, the function is continuous, as you saw from here. It is a continuous function, but the function is not differentiable at every point. At that peak value, it is not differentiable. So be very careful. You know, Rolle's theorem tell you, well, yes, it is a continuous function, but only if differentiable. At every point on the open interval. So let's move on now to the mean value theorem. Okay, another theorem we will use, the mean value theorem. So this theorem states that if f is continuous on the closed interval and differentiable on the open interval, then there exists a number c such that f prime of c is f of b minus f of a divided by b minus a. Now, you've seen this formula here before. Yeah, you've seen that before. Also, you've seen that in pre-calculus. So the mean in the mean value theorem refers to the average rate of change. So you remember that from pre-calculus, okay? Average rate of change. Okay. Since the mean value theorem, or the rate of change, is something that we've looked in the past, we'll just do some examples to see how it applies to us in calculus and what it's really saying. So if we look at an example here, okay. So what we want to do is determine whether the mean value theorem can be applied to f on the closed interval -1 to 1. If it can, find all value of c in the open interval -1 to 1 such that f prime of c is equal to f of b minus f of a divided by b minus a. So let's look at this really. What are the steps involved? These two theorems are not very difficult theorems. Okay, so it's just an understanding of what they are. Okay, so what we should do is, what is f prime of c here? Okay, so f prime of c will be f of b. Therefore, our f here, I didn't give you the f of x, so let's give you given here, given f of x is equal to, let's look at the function x cube plus 2x. Okay. So first we want to figure out what is f of a and what is f of b, because we need that in the formula here. Okay. So f of a would be f of minus 1, and f of b would be f of 1. So f of minus 1 will be minus 1 cubed plus 2 times minus 1, which is minus 1 minus 2. So this is negative 3. So f of minus 1 is equal to negative 3. And then f of b, which is positive 1, this is equal to 1 cubed plus 2 times 1, which is equal to 1 plus 2, which is equal to 3. So f of 1 is equal to 3. Therefore, f prime of c will be f of a, which is, I wouldn't write f of a, let's just write negative 3. This is negative 3 minus f of b, which happens to be 3. Okay. F of b, sorry, f of b, this is my f of b, which is equal to 3 minus f of a, which is my f of a here, negative 3, divided by b. The value of b we know was 1, and the value of a is negative 1. So simplifying this, we have 3 plus 3 over 1 plus 1, which is equal to 6 over 2, which is equal to 3. So f prime of c is equal to 3. Now, so far what I've learned here, the only thing that this tells me, okay, and understand, try to understand, this tells us that the slope of the line that passes through the point negative 1, negative 3, and 1, 3 is 3, right? This 3 here is this 3 here. Now, if we look at the graph of this, so what I'm going to do is take my handy dandy graphing calculator, and I'm going to graph that function, okay, just to show you what's happening. This is a rough sketch of the graph between minus, so this is just a piece of the graph. Now, what I found out that if I draw a line from minus 1 to 1, okay, that the slope here, m, is equal to 3. That's all it tells me. Right? So keep in mind that that red line is some secant line. Okay? That line, that diagonal line, that straight line is some secant line. So the slope of this red line that I drew is m equals 3. Okay? Now that red line is a secant line. So the line that we're really talking about here, that's a secant line. Now let's take f prime. What is f prime of x? Well, f of x was given to us as x cubed x cubed plus 2x, x cubed plus 2x. F prime of x will be 3x squared plus 2. So f prime of x equals 0, meaning that 3x squared plus 2 is equal to 0. So 3x squared is equal to negative 2. So x squared is equal to minus 2/3. So x is equal to plus or minus the square root of negative 2/3. In actuality, there's a little error here because our f prime was equal to 3. So we have to set f prime of x equals 3, okay, not 0. So f prime is 3x squared plus 2 equals 3. So 3x squared is equal to 1. X squared is equal to 1/3. X is equal to plus or minus the square root of 1/3. Okay. So we have two values of c here. So in the interval, the open interval, okay, -1 to 1, you can conclude that c equals to the square root of 1/3 or c equals negative square root of 1/3. Okay. Now, what does that tell? Well, if you go back, the square root, just to give you an example of the decimal, square root of 1/3 in a decimal. We're not going to write the decimal, but I just want to give it square root of 1/3 is approximately 0.577. So that brings me to 0.577, somewhere here and somewhere here. Okay. At those 2 points, what you will see is that if you look at that green line and you look at this green line here, okay, clearly you can see that those are tangent line. So in the interval, the open interval, okay, you can conclude that c equals 1/3 or c equals minus 1/3. So just as a little hint, do not make this mistake as because we're coming from a different section, not equal to 0. Okay, it has to be equal to this number here because this is your f prime of c. Yeah, f prime of c here. All right, so that's our example on the mean value theorem. Okay. So just to recap, Rolle's theorem, right, tells you that if the function is continuous on a closed interval and f of a is equal to f of b, then there is some c, yeah, there's some value c, and it is continuous and differentiable at every point where f prime of c is equal to 0. Yeah. The mean value theorem says that if S is continuous in the closed interval and differentiable in the open interval, there exists a C where we know that we have the slope, okay, of that line. And the slope of the secant line is the same as the slope of the tangent line. And that's all we have to cover in this section.